Going to do another short video for you today about calculating average atomic mass from what you know about isotopes. So you'll need to get your notes out, move to the next section about calculating average atomic mass. When we talk about the average atomic mass of an element, it turns out that every isotope of an element contributes to the average atomic mass. So we talk about the protons and the neutrons providing the majority of that mass, but if I have more of one isotope than I do of any of the others, it's going to provide a greater weight to that total average atomic mass. So think about it the way you think about calculating a GPA. If a student has 4 A's and 3 B's and 2 C's and 1 D, we have a total number of grades, right? We've got 10 grades. But I don't take 10 and divide by 10 to get my average for my GPA. So what I'll do instead is multiply those 4 A's times 4, and that'll give me 16. And my 3 B's times 3, which will give me 9. And my 2 C's times 2, and that will give me 4. And my 1 D times 1 to give me 1. So then I end up with 16 and 9 is 25, and 4 is 29, and 1, 30, right? So then if I take 30 and divide that by 10 grades, then I end up with a GPA of 3.0. All right? And so when you look at that person's grades, you know that they're going to have a higher GPA because they've got more A's and B's, as opposed to somebody who would have a GPA that's lower if they have more C's and D's. And that's what we call a weighted average. So I have to have an element that's got different numbers of isotopes. Suppose we go with carbon, and we know that carbon-12 is about 98% or so of our isotopes, and our carbon-13 is only about let's say 1.2%, or no, 1.8% or so. Getting my numbers mixed up. And then we talk about carbon-14, and we say that that's about 0.2% or so. Then we know that when we calculate our average mass, the mass of carbon is going to end up being much closer to 12 than it is to the carbon-14. Okay, and so when you check the periodic table and look at the average atomic mass, you'll see that its average atomic mass is 12.011, and that's because more of those carbon-12 atoms contribute to the mass than the carbon-13 or carbon-14. So we have a specific equation that we use to calculate average atomic mass, and that average atomic mass is written like this. Atomic mass is equal to the sum of, and this is the Greek letter sigma, and it means to sum. So we're going to do the sum of the mass of isotope 1 times what we call its fractional abundance, and then we'll do that plus the average atomic mass for isotope 2 times its fractional abundance, and isotopic mass 3 times its fractional abundance. And so what we really end up with is this series of values that we've multiplied together. And the more you have of isotopes, the more of those you have to include in your equation. So we're just going to look at an example that's only got a few isotopes. You know, if you had 20 isotopes, this would be a great big long equation. Now, the way that we write this with this equation is that we talk about fractional abundance. And fractional abundance really has the same meaning as percent abundance. It's just that we've taken that percent abundance and divided it by 100 to get to get a fraction, to get a number less than 1. So if I have 98% fraction or percent abundance and I divide that by 100, then I get 0.98, and that's my fractional abundance. Okay? So let's look at an example, and then once we look at that example, I'm going to turn you loose and have you work some problems today as well. And then hopefully my knees and my muscles in my leg are going to be better, and I'll be back on Wednesday. Okay, so let's look at an example. It says an example has two naturally occurring isotopes with the following masses and abundances. What's the atomic weight of the element, and what's the identity of the element? So if you look, we have two isotopes. There's isotope 1 and isotope 2. Isotope 1 has a mass of 84.9118, and those are measured in what we call atomic mass units, or AMU. And isotope 2 has a mass of 86.9092. Both of those have a specific fractional abundance, and you'll notice if we add those two values together, we get 1.000. Actually 0. Okay? So fractional abundances are very similar to the percent abundance. We said isotope 1 is 72.15%, and isotope 2 is 27.85%. So if I want to calculate the average atomic mass of this element, I'm going to start out with isotope 1, and I'm going to measure that 84.9118 atomic mass units times its fractional abundance, which is 0.7215. And to that I'm going to add the average atomic mass of my second isotope, which is 86.9092 atomic mass units, times its fractional abundance, 0.2785. Okay, so I'm going to do a little bit of calculator math. If I do 84.9118 times 0.7215, I want to go 4 significant digits on that, and I'm going to get 61.26 for this value. And then for my second isotope, I'm going to do 86.9092, multiply that by 0.2785, and get 24.20, still two significant figures. Those are also AMU, and when I add those together, 61.26 plus 24.2 is 85.46 atomic mass units. Alright, so then we say that our average atomic mass of that element is 85.46 atomic mass units, and when you look at the periodic table to figure out what that mass is, you're looking for the element that is 85.46, or as close to it on the periodic table as you can see. And I'm kind of killing time because I'm scrolling down to get my periodic table on my computer because I don't have a periodic table in front of me. And I am going to say that that's going to be somewhere along the lines of, oh, you already know what it is. I don't know what it is. It's somewhere along the lines of, say, rubidium. That looks pretty close, doesn't it? So the element is rubidium, and we've calculated its average atomic mass from the masses that we know of its isotopes. Now remember, we talked about the elements, and we get past uranium and you start seeing those elements and their atomic masses reported as whole numbers with the parentheses. And what that means is that all we know the mass of are maybe the most common of the isotopes or the most abundant of those, and don't know masses or haven't identified all the other isotopes of that element. And so we can't calculate its average atomic mass because we don't know enough information yet. Okay? So you take a little bit of time this morning and work on, or this afternoon, I guess, and work on a few more problems for me. And then tomorrow when I come back, we will actually calculate the atomic mass of bemium. Okay? I'll talk to you later. Bye.